So I should find a large region of your graph that doesn't have this line business.
Okay, so let's get started. So welcome to the session dedicated to quantum DCP conjecture. It's our quest to encode computation in the most robust form you can imagine. So we'll start with Louis Golowich, who is a grad student here at UC Berkeley. We will not take a break before the next talk. We'll just have the next talk right away, and then take a break, two more talks, and then we'll have a late lunch from 1 p.m. and then there'll be a free afternoon. That's why. So the hope is that you enjoy and collaborate and discuss. Okay. So with that, Louis, please.
Yeah, I'll be talking about how to get NLTS Hamiltonians and also a bit about some SoS lower bounds from low-rate quantum LDPC codes. And this is joint work with colleague Hoffman. So to start, I'll just give some brief background on quantum LDPC codes because these will kind of underlie almost everything I'm going to talk about. So the general setup in quantum error correction is that we have some k message qubits or logical qubits, which we want to pass through an encoding function to get some larger number n of physical code qubits, with the property that if we experience corruptions on some bounded number, say up to d of these physical code qubits, we can perform some stabilizer measurements and recover the original message. So what that looks like is that we'll measure some Pauli operators. For instance, the tensor product of these three Pauli x's. We'll then measure maybe the tensor product of these three Pauli x's and measure maybe some Pauli z's and do this type of measurement and use these measurements to ultimately perform some post-processing and recover the original message. Now the LDPC property here just says that these measurements are low weight. So kind of each of these Pauli stabilizer measurements only involves a constant number of qubits. And constructing these LDPC codes with low weight stabilizers was a big open question, at least in terms of getting optimal parameters, which was recently resolved by like a very beautiful line of recent work. So asymptotically good quantum LDPC codes are these quantum LDPC codes that have constant rate. So the ratio of the number of physical to logical qubits is a constant. There's a constant space overhead in the encoding. Constant relative distance, so we can recover against errors acting on a constant fraction of the physical qubits. And constant locality, so all the stabilizers have constant weight. And intuitively, we can see that these three properties are very, very powerful for error correction because it means we can perform all of these low-weight stabilizer measurements, each of which will kind of only touch a constant number of qubits, so not introduce too many additional errors. And collectively, we can correct against a linear number of errors with a constant space overhead. So the construction of these asymptotically good qLDPC codes was a major breakthrough for error correction. And the theme of this talk is that kind of building on some other recent works, these codes have also led to breakthroughs in complexity theory. So most of what I'll talk about is kind of a follow-up to this breakthrough work by Anshu, Breuckmann, and Nirkhe, which showed that NLTS Hamiltonians can be obtained from these good quantum LDPC codes. And I'll define what all these things mean in a bit. But even before this work, there was actually another application to classical complexity theory, which was arguably a breakthrough in itself, which is kind of constructing these explicit lower bounds against a classical algorithmic framework called the sum of squares SDP. And somehow these quantum LDPC codes again led to kind of these hardness results in classical complexity theory. So what I'll be talking about today is kind of a couple of maybe modest improvements to both of these results. So on the NLTS side, we showed that kind of the asymptotically good condition is stronger than we need to get NLTS Hamiltonians. It's actually sufficient just to have the codes be linear distance, but they can have any positive dimension. So they just need to really encode a single logical qubit. And on the SOS side, we're going to kind of remedy a slight weakness in the explicitness of these bounds. The original bounds by Hopkins and Lin were only weakly explicit. We'll make them strongly explicit, and I'll later say exactly what that means. But I guess both of these improvements are kind of in the theme of using low-rate codes. So that'll be, I guess, a big theme of this talk. Now, along the way, I'll also describe a construction of these kind of low-rate quantum LDPC codes, which we'll call planted quantum LDPC codes. And these are quantum LDPC codes where we have linear distance, and we're guaranteed to have positive dimension by a method that doesn't simply count parity checks. So ordinarily, I'll go into details on this later, but ordinarily to bound the dimension of a quantum LDPC code, or at least for these asymptotically good qLDPC codes, we simply count the number of qubits and subtract off the number of stabilizers. But this bound isn't always tight, and we show that we can actually use a completely different method to ensure just some positive dimension. And there's actually some applications of this, why we might want to do this, which I'll again get into later. So I'll now be talking about NLTS Hamiltonians, and specifically how we can get them from just any linear distance code. So the motivation for this work comes from the study of hard local Hamiltonians. So we can kind of view local Hamiltonians as a mountain, where as we go up the mountain, things get harder. And by things get harder, I mean kind of it gets harder to compute things about low energy states of the local Hamiltonian. So actually, NLTS Hamiltonians will be closer to the bottom of the mountain in the picture I'm going to draw. And NLTS Hamiltonians, or no low energy trivial states Hamiltonians, are simply local Hamiltonians where all low energy states require super constant circuit depth to construct. So a family of local Hamiltonians is NLTS if there's no constant depth circuits that can construct low energy states for all of these Hamiltonians. Now, so I guess the reason I put this closer to the bottom is because the notion of hardness is kind of super constant circuit depth, which in the grand scheme of things might seem like kind of the not the hardest notion of hardness, I guess. Indeed, closer to the top of the mountain, we have quantum PCP Hamiltonians, which are defined to be families of local Hamiltonians, for which it's actually QMA hard just to compute an approximation of the ground energy, even just like a constant factor approximation of the ground energy. So kind of it's a wide open conjecture called the quantum PCP conjecture that there actually exist families of quantum PCP Hamiltonians. So the QPCP conjecture, in other words, states that kind of it's QMA hard to even get a constant factor approximation of the ground energy of local Hamiltonians. Now, we should expect kind of implications to point down the mountain. And indeed, if we have a quantum PCP Hamiltonian, it's necessarily NLTS, assuming that QMA is not equal to N. So I guess this is confirming our intuition that kind of these things up here are harder than the things down here. So,
So it's not true that like quantum PCP applies NLTS. It's like normally you need to assume this.
I mean, I guess if BQP,
It's not formally stronger. It's like
yeah, I mean, I guess if like BQP and QMA are all the same, they're all equal to P, then I think everything collapses. So,
okay.
well, we should expect to need some sort of. But yeah, it's not unconditional.
I'm sorry, is QMA equals to P implied that? Because one thing is like being able to prove the ground energy, and the other thing is constructing the ground state, which is the NLTS, right?
Right, so I think if you have an NP, right, yeah, I guess it might not go both ways.
So you're saying that if QMA equals NP, then it's not clear whether you can still consider the ground state.
That's my question. Yeah.
Right.
Or a lower energy state.
Yeah, I think that's a good point. Probably it's not clear.
Yeah, just not it's one direction.
Thanks, yeah.
But QMA is not evidently right.
Old state.
Yeah, I think maybe the statement I was trying to say is that kind of if QMA like equals B or something, then I think we should expect quantum PCP to kind of be a tautological statement. So it shouldn't really imply anything. Great. So, so in 2022, Anshu, Breuckmann, Nirkhe constructed kind of the first known families of NLTS Hamiltonians. This was like a big breakthrough result. Their construction was based on quantum LDPC codes, as I'll get into later. And this was kind of one of the most important instances of progress we have towards the ultimate goal of constructing quantum PCP Hamiltonians, which are conjectured to exist by the quantum PCP conjecture. So ideally, we'd kind of take these NLTS Hamiltonians and slowly make them, or maybe quickly, but somehow make them harder to get to our goal of quantum PCP Hamiltonians. This seems, I guess, like a promising direction, but what I'll describe in this talk is something that's not quite in this direction. It's something kind of going sideways. I'm going to tell you how we can get some more NLTS Hamiltonians, or how we can get NLTS Hamiltonians from some kind of restricted or relaxed assumptions on the codes. But I guess this can still be viewed as, in some sense, progress towards the goal, because kind of the more constructions we have down here, the more degrees of freedom and the more flexibility we have in order to kind of find a construction that might generalize towards something higher. At least that's like one motivation for why we might want more of these NLTS Hamiltonians. So I should now define what are NLTS Hamiltonians. So NLTS stands for no low energy trivial states. And these NLTS Hamiltonians are simply a family of local Hamiltonians. So we call a local Hamiltonian is just a Hamiltonian that's a sum of terms, each of which acts on just a constant number of qubits. So it's a sum of local terms. And we want a set of local Hamiltonians with the number of qubits going to infinity, along with some constant epsilon, some positive constant epsilon, such that as n goes to infinity, you need super constant circuit depth to construct epsilon low energy states to these Hamiltonians. So the family's NLTS, if there's no family of constant depth circuits that can construct states rho for all of these Hamiltonians H, such that all of these states rho have energy at most epsilon with respect to the Hamiltonians. So this is the definition of an NLTS local Hamiltonian family. And how can we expect to kind of prove that a family is local Hamiltonian? Well, we need a way of getting these super constant depth circuit lower bounds. We need a way of showing that somehow these low energy states of these Hamiltonians cannot be constructed by constant depth circuits. And the approach that I guess was first taken by Elder and Harrow and then subsequently built upon by ABN was that we can kind of get these circuit lower bounds from a notion called well-spreadness. So I'll now define this notion. Let's say we have some state rho, which we want to measure in the standard z basis. So we get some, the output is going to be some probability distribution over length n bit strings, or over the space f2 to the n. And let's suppose that there's some set here that we land in with constant probability, and also some set over here of bit strings that we land in with constant probability, such that these two sets have linear Hamming distance. So essentially, any point in the set over here and any point in the set over here differ in a constant fraction of their components. So if the measurement distribution of rho has this property, it has these two kind of far apart constant probability clusters, we say that rho is well spread. And if rho has this well spreadness property, it necessarily follows that every circuit constructing rho has depth at least logarithmic in the number of qubits, and in particular has super constant depth. So this is basically saying kind of well spread states rho in the sense of their measurement distributions looking like this necessarily requires super constant circuit depth to construct. Great. So now we just need to construct a family of local Hamiltonians such that all the low energy states are well spread. That will immediately imply the circuit lower bounds we need for NLTS.
Is it clear why that's true?
Why this implication is true? So yeah, I don't think it's not like direct. I think the original proof, it was proven by Elder and Harrow. I think so for intuition, you can kind of intuitively see that kind of, if we do something trivial, like so we start in the all zero state, which isn't well spread. We can apply Hadamards everywhere. That will be also just not well spread because it's uniform. And intuitively, both of these you can think of as kind of well-connected graphs. If we kind of connect nearby bit strings in the measurement distribution, one of these is like the complete graph. On 2 to the n vertices, one is a single point. And so the proof kind of shows that this this kind of well-connected, like this expansion property of the graph in the measurement distribution, we can't kind of build up poor expansion in low depth. So that's the intuition. The proof, it's not super trivial.
If you only care about super constant depth, does the Hamming distance still have to be n, or can it just be like anything super constant as well?
Yes, that's a good point. So the Hamming distance does not need to be n.
More than root n.
Yeah, I think root n is the number. So that's actually a good point, because later on when we're talking about codes, it may seem like we only need codes of distance root n, because this only needs to be root n. But for a different reason, we're actually going to need linear distance codes. But in this point, it doesn't need to be linear.
So can you say analog this Pascal statement, say if I have a Markov chain which is generating some property distribution, so if it has a property like this, can I say anything on the runtime of that or convergence rate of that chain, saying that it has to be pretty long?
Interesting. I see. So you're just saying use this in the context of
Yeah, rather than like saying about like quantum gates, can I make an analogous statement which is like classical random processes?
That's interesting.
Property distribution, right?
Yeah, I'll have to think about that more, but it's an interesting point. Great. So we just need to construct local Hamiltonians such that all low energy states have this well spreadness property. Now, what local Hamiltonians have this property? The answer is, or one answer is kind of qLDPC code Hamiltonians. So I should now describe quantum LDPC codes before I can say the formal statement of what conditions we need the code to satisfy to have this well spreadness that implies NLTS. So I guess I'll give a kind of a brief description of some more involved structure that qLDPC codes have. So in general, a qLDPC code, or at least a CSS qLDPC code, can be defined by a tripartite graph where we have the code qubits in the middle, the z stabilizers on the right, and the x stabilizers on the left. I guess I should say stabilizer generators. So each vertex on the left defines a stabilizer, which is given by the tensor product of Pauli x's on its neighbors, on the qubits that it neighbors. So this vertex here represents the tensor product of these 4 Pauli x operators, which is an x stabilizer. This vertex on the right represents the tensor product of these 4 Pauli z operators. It's another stabilizer. And you can see that kind of this x stabilizer and the z stabilizer intersect at exactly 2 points, at this point, and at this point. And indeed, if a Pauli x and a Pauli z operator intersect an even number of positions, they're going to commute. And this is actually what we want. We want all the x stabilizers to commute with all the z stabilizers. So this tripartite graph has the property that every vertex here and every vertex here share an even number of neighbors. Now, if we have this property, we get a well-defined CSS code from this, a well-defined quantum code from this graph. And we can use this code to encode at least the number of qubits or a number of logical operators, or a number of logical qubits that's at least the number of qubits minus the number of stabilizers. So the dimension of the code is bounded by this. When I say a logical operator, I just mean some Pauli operator that commutes with all the stabilizers, but is not itself a stabilizer. So for instance, we could check that the tensor product of these two Pauli z's is a logical operator. And really, this is like these are kind of the undetectable errors. They're the Pauli operators that if they occur as an error, they commute with all the stabilizers, so none of the stabilizer measurements will detect this error, but it's not itself a stabilizer, so it is imposing some error on the code state. And naturally, we define the distance of the code to be the minimum weight of a logical operator, the minimum weight of an undetectable error. Finally, the locality of this code is simply like the degree of this graph. It's the maximum weight of any of the stabilizer generators. So with this, we can define the code Hamiltonian. It's kind of the average of an x term and a z term, which look like this. Rather than kind of going through this definition, really I should just say kind of this code Hamiltonian imposes that all the stabilizers are enforced. So if we have some code state, which is in the +1 eigenstate of all of the stabilizers, it'll be in the ground space of this code Hamiltonian. If we have some state that's pretty far from being a code state, so say it violates all of the stabilizers, it's in the -1 eigenstate of all the stabilizers, then this state will be kind of, it will have energy 1 with this Hamiltonian, so it'll have the maximal possible energy. So this Hamiltonian really measures the fraction of stabilizers that kind of stabilize our given state. In other words, it kind of measures the relative syndrome weight of a state we pass through. So I've told you that these qLDPC code Hamiltonians will be NLTS if the code has certain properties. I'll now say what these properties are. So Elder-Haro in 2017, who I guess first used the approach to show that if the code has linear distance, any positive dimension, and a very strong property called local testability, then the code Hamiltonian is NLTS. I won't get into this local testability property yet, but I'll say kind of it's very strong, and we still don't know how to construct these codes because this property is so strong. Now, ABN 22 resolved this issue by showing that if the codes have linear distance, now linear dimension, so that's, I guess, a stronger requirement, but a weaker notion of testability called this clustering property, then kind of if the code has these three properties, the Hamiltonian is NLTS, and these codes actually are known to exist. So kind of this line of work I mentioned resulting in these breakthrough constructions of good qLDPC codes have all of these properties. So what I'll now describe is kind of how we can get the best of both worlds here. So we can get NLTS Hamiltonians from codes of linear distance, any positive dimension, and just this weaker testability property called clustering. And I've added in kind of this work here because at the end I'll describe how we can actually get codes that seem not to have linear dimension, but are still LDPC and have linear distance. Great. So what is this clustering property? It's really the only thing I haven't yet told you what it means in this picture, like the last ingredient we need for NLTS. So let's consider again measuring some code state in the X or in the Z basis. We get a distribution over classical bit strings. And if we're measuring a true code state row, so it's in the ground space of the code Hamiltonian, then essentially our measurement distribution will look like this. We'll have a bunch of individual bit strings. There will be some that are close together, corresponding to two code states that differ just by a stabilizer. And then there will also be some that are far apart, actually linearly far apart, corresponding kind of the linear distance of our code. If we now relax to just looking at all the low energy states, so now rho is energy at most some constant epsilon in our code Hamiltonian. The clustering property says that the measurement distribution now looks like this. It's kind of supported in a bunch of distinct far apart clusters within f2 to the n. So here you can see that some of the clusters are basically just kind of little balls around the true code states, And this is what we should expect. Kind of, if we take a true code state and perturb it a little, we won't increase the energy that much. But this clustering property also allows for these, what I guess I'll call these phantom clusters, which are kind of clusters of bit strings that are kind of close to each other but far from everything else. And yet these clusters kind of don't contain any true code states. They only appear when we start looking at low energy states. And so if the measurement distribution is supported in clusters of this form, like true clusters and phantom clusters, we say the code has the clustering property. And this turns out to be sufficient to conclude NLTS. So also it turns out that this clustering property, at least as far as I know, is achieved by all known linear distance qLDPC codes. So kind of the last step we need is this implication, that clustering implies well-spreadness. Because we already saw that well-spreadness implies super constant circuit depth that we need for NLTS. So all we now need to do is show that no low energy state of our linear distance qLDPC code Hamiltonians is concentrated within a single cluster. Because actually, if we're spread across at least two different clusters, then kind of we know we're well spread because all these clusters are far apart. So the only way we could not be far apart is if the entire measurement distribution is concentrated in a single cluster. So the final ingredient that we need to show this, that we have no concentration within a single cluster, is an uncertainty principle. So this is again the approach used by LDPC in 2017, Anshu, Breuckmann, Nirkhe. And the idea is that if we measure our low energy state rho in both bases, so in the x basis and in the z basis, we want to argue that kind of our measurement distribution in at least one of the two bases will not be concentrated within a single cluster. Because then we can use that basis to apply our circuit lower bound. So we want to show that there do not exist kind of a single cluster S in the x basis and T in the z basis, such that there's extremely high probability, or such that there's a high probability of landing in both either S or T when we measure in the respective x or z basis.
And those clusters don't have to be, they can be phantom clusters. Although in this picture.
Yeah, so, oh yeah, I'll get to that.
Okay.
So, yeah, thanks. That's actually exactly where I'm going. So, right, so as drawn, they could be any cluster, they could be phantom clusters as well. But for LDPC in 2017, they actually wanted the property that S and T can be decoded to code states. So basically, as I mentioned, there's some uncertainty principle going on. And the uncertainty principle that LDPC used, it basically involves kind of anti-commuting logical operators from the code. And the upshot is that they had the desired uncertainty principle that these ST cannot exist, as long as all the clusters, in particular both S and T, kind of can be decoded down to true code states. Specifically, we need all the points in S and all the points in T to each be decodable down to true code states that are like logically equivalent to each other. So for this reason, they need to assume that there's no phantom clusters, because you can see kind of for all these true clusters around true code states, there's kind of the natural decoding algorithm that you could just naturally come up with, kind of just decode this entire cluster down to one of the true code states in that cluster. But for these phantom clusters, like they contain no code states, so we can't really just decode them to true code states. And for this reason, the LDPC argument kind of just need to assume there's no phantom clusters. And the property of having no phantom clusters is almost the definition of local testability that I mentioned earlier, so that's why they need to assume that we have locally testable quantum LDPC codes. Anshu, Breuckmann, Nirkhe resolved this issue by saying kind of forget the logical structure of the code, forget decoding, we're just going to look at the size of these clusters. And what they argued is that kind of if we have kind of a small cluster, so a small set in the x basis and a small set in the z basis, and in particular, if the product of the size of these sets is much less than 2 to the n, then kind of it's impossible for any state rho to have high probability of landing in S in an x measurement and in T in a z measurement. So they just use kind of a completely different uncertainty principle. And all they need to do is kind of show these clusters aren't too big. And for that, they assume that the code is linear dimension. So I guess the only new thing I'm going to tell you is that kind of phantom clusters are actually OK. So we can actually go back up to this Elder-Harrow argument and argue that kind of they didn't really need to assume no phantom clusters. There's a way to get the decoding to work with these phantom clusters. And kind of the key observation for this is that the phantom clusters actually respect the action of the code's logical operators. So you can see in these pictures, the way I've drawn it, kind of the phantom clusters, they have the same, like, they're kind of just translates of the true code states. They have the same linear structure of as the true code. And this is actually very accurate. Like in real codes, these phantom clusters kind of respect the exact same logical operators and the exact same linear structure as the true code. They're just kind of shifted by some linear distance. But what this means is that we can kind of fudge a decoding algorithm where we start with just some arbitrary phantom cluster, decode it to some arbitrary true code state, and then we just kind of extend this process by linearity to all the phantom clusters. And for each one, we decode it to some arbitrary true code state. It's not going to be nearby, so it's not decoding in the standard sense, but nevertheless, it's kind of a well-defined map where we just need to do some syndrome measurements, and then we can perform this decoding. And somehow this decoding channel is enough to run the Elder-Harrow argument. It's enough to plug into the Elder-Harrow uncertainty principle and conclude that we can't kind of be concentrated within a single cluster in both bases. Yeah, so I guess really all we need to observe is that kind of phantom clusters respect the code's logical structure.
So a little bit more precisely, what happens? So if you apply logical operator, the phantom cluster goes to some other phantom cluster?
Yeah. Yes. And so I guess phantom clusters come in these kind of, there's different types of them, and for each type, we basically get a copy of the code's logical structure.
So can you label these phantom clusters somehow in relation to the code word? Is there like an archetypal element or something?
Yeah, so I think this is, again, kind of, there's different types. So if we choose one phantom cluster, then we can indeed kind of label all the shifts of this cluster according to the code's logical operators. But we may have like different copies. So I guess each like type of cluster induces kind of like a copy of the code's logical structure. And we can.
One other question. I think there are like many phantom clusters, like 2 to the like order n phantom clusters per real cluster, right? So how do you do this mapping? All of this is converging. That seems non-unitary to me.
Oh yeah. So I guess decoding in general is non-unitary.
Okay.
So yeah. So we kind of imagine there's an additional syndrome measure, a syndrome register, which we kind of put the syndrome measurement into. And I guess based on the syndrome register, we can perform kind of the decoding. So the decoding is unitary on the combination of the code register and the syndrome register, which is actually the same setup as just ordinary decoding.
Sorry, when you say choose phantom state, are you actually implying something about a decision type of problem, or are you just taking an example?
Sorry, did I say choose? Oh, sorry, yeah, no, no decision type problem. There are arbitrary, like non-canonical choices in this decoding algorithm, but it doesn't have to be algorithmic. Like this is just for the proof. So it can be arbitrary.
So are you implying an example that
Oh, no, sorry. So yeah, literally I'm saying we're defining some decoding algorithm where I guess there's like an axiom of choice almost, but everything's fine. So we fix an arbitrary phantom cluster, which I guess we choose, but we can choose it to be anything, like the first one we come up with. We define how we decode that, and then by linearity, that extends to a lot more phantom clusters. So sorry, yeah, no decision problem. So I guess just to recap, these are the 3 properties that qLDPC codes previously were kind of, these are the three properties that were previously used to show NLTS for qLDPC code Hamiltonians. In particular, using linear dimension to get well spreadness. Kind of all I've described to you so far is just kind of how to bypass this linear dimension requirement. So I've told you why we don't need linear dimension. But if you think about it a little more, kind of linear dimension is a good thing in general in error correction. It means we can encode a linear number of qubits. So I've told you kind of we can get NLTS Hamiltonians from worse quantum codes, but I also haven't even told you that these codes exist. Because actually, basically all the previously known good qLDPC codes automatically had linear dimension. So can we even construct any quantum LDPC codes that don't have linear dimensions to kind of instantiate the kind of relaxed NLTS construction I've just told you? It seems that the answer is probably yes. It turns out this probably, for the applications I'm going to describe, this probably isn't really a problem. So what this means is that we can indeed construct codes where they naturally seem to have dimension 1. We can only prove they have dimension 1, but it's, I guess, technically possible they could have linear dimension. So the intuition comes from what I'll call planted classical Tanner codes. I'll give the classical intuition because I think it's simpler and has the key ideas for the quantum case. So classically, a Tanner code is described by two pieces of data: an expander graph, just a graph that's sparse but well connected, and a constant-sized inner code C sub n. Given these two objects, we can construct a classical Tanner code C, which has code words corresponding to labelings of the edges, to the labelings of the edges of the graph with bits. And kind of an edge labeling is a code word if every vertex, or the local view of every vertex lies in the inner code. So for instance, this vertex up here, it sees 1, 1, 0. So if 1, 1, 0 is in the inner code, we pass the checks at this vertex. If that's the case for every single vertex, kind of globally, we have an edge labeling that's in the code C. So how do we ensure positive dimension for these classical Tanner codes? Ordinarily, we count linear constraints. We have some number of variables corresponding to the code bits, some number of constraints corresponding to these inner codes at the vertices. If the difference is positive, we have more variables and constraints, so we have non-trivial code words. What I'm claiming we can do is something much simpler. If we just want a single non-trivial code word, we'll literally just plant the all ones code word in the code. So if we require that the inner code contains the all ones code word, then globally, if we just take the all ones code word or the all ones vector, every vertex sees only ones on its incident edges. So we just trivially have this all ones vector in our code. Now I'm saying that we do this quantumly. It's actually a little more complicated. Classically, it's basically trivial. Quantumly, due to degeneracy issues, you have to be a bit careful. But ultimately, we get these planted quantum Tanner codes such that they're essentially explicit linear distance quantum LDPC codes that are guaranteed to have these two logical operators. They have an X operator corresponding to applying Pauli X to every single qubit. And they have a Z operator corresponding to applying Pauli Z to every single qubit. So they're these extremely strongly explicit, like basically trivial logical X and Z operators. There may be other logical operators as well. Depending on how we choose parameters, we can try to make it so there are or so there aren't. But why would we want to do this? Kind of why would we want to reduce the rate of this code down to like 1, or dimension down to 1? So I'll describe these kind of in increasing order of maybe interest, just to build up. So kind of the first thing, which maybe is interesting, maybe not, is just these, I guess, by everything I've told you, give more NLTS Hamiltonians. Maybe kind of for the error correction side, they give linear distance positive dimension codes without resorting to parity check counting. So ordinarily, we bound dimension as the number of qubits minus the number of stabilizers. Here we just say dimension's always positive regardless of the number of stabilizers. This is kind of might be a useful knob to turn for some error correction applications. And in particular, we get these strongly explicit logical operators consisting of all x's or all z's. And I think there's kind of two potential applications of this.
Sorry, don't you have to be careful that your logical x and z don't commute? Because you have like x tensor n and z tensor n, but that doesn't necessarily span the code space, right? Because they might be commuting operators.
Right, so n is going to have to be odd here.
Oh yeah, okay, fair enough. That's a good solution.
No, that was actually one of the technicalities.
Yeah.
Because you get expanders with odd number of vertices.
Yeah, okay.
Yeah, that's a very good point. Right, so once we have this, we may get applications to fault tolerance. I've kind of heard this question floating around recently, like, can we get a linear distance qLDPC code with maybe a single logical operator with like very explicit kind of poly structure, like very explicit expression for it? In the context of like, I don't know, self-correcting memories or transversal gates, it seems this type of thing maybe could be useful. So I think it's nice to know that this is something we can do. And kind of the last thing I'll talk about is how we can use this to get like a concrete application, which is these strongly explicit SoS lower bounds. So very briefly, sum of squares or SoS is a powerful classical algorithmic framework, and we naturally want to understand its limitations. Now, the known hard instances for SoS, so the known problems for which SoS cannot achieve better than a constant factor approximation, were essentially all random. Until this work of Hopkins and Lin that I mentioned at the start that used qLDPC codes. I'm definitely brushing over kind of a bunch of important works on SoS lower bounds, but really, in some respect, their work was like an exponential improvement over what was previously known. And the one downside is that kind of the whole point of this was explicitness, but it was actually only weakly explicit. They need to run Gaussian elimination to find some non-trivial, like logical operator or some non-trivial code word in a qLDPC code. Somehow, given this non-trivial logical operator, they were then able to get the SoS lower bound. So kind of planted quantum Tanner codes immediately resolve this issue because they always contain like the all ones logical operator, like the all x's or all z's. So we can just plug this into the Hopkins-Lin construction and get, I guess, make their weakly explicit SoS lower bound strongly explicit. I guess that's kind of one application where kind of a direct application of these planted codes. So
what is the problem that you're giving the lower bound for?
Right. So here it's like maybe max 3 XOR or max 3 Lin. So kind of maximize the number of satisfied equations from a set of like, linear equations over F2, each of which has the sum of 3 variables equals something.
And so those clauses are going to be the constraints in the code.
Yeah. We basically take like the stabilizers, so the parity check matrix for like the X code, and use that to exactly get the clauses. We actually take the transpose. But that's it. Thank you.
Yeah, so are you making any assumptions if you have any predictions about like why or why not you're going to interactive property Sorry, I mean, so are you looking at things like clearly about how this is or is not